Hello, everybody. Welcome to our Afternoon Astronomy Coffee Hangout. My name is Tony Darnell, and I run, work, and play at deepastronomy.com. And this week, we've got a really great hangout planned for you. We're going to be talking about the venerable Cassini mission around Saturn, which has begun, I think, back in April, its grand finale. And we're going to be talking about what that is and why the mission will end the way it is, along with all of the great science and a look back at some of the things that Cassini has taught us. And we've got members of the Cassini mission here from JPL here to talk about all of these great things. But before I introduce them, I have to bring up my very good friend and colleague, Dr. Carol Christian. Hi, Carol.
Hello, hello.
It's good to see you again.
Happy 40th anniversary to Star Wars.
Has it been 40 years?
Yay.
Yay.
Oh, 40 years. Man, why? You didn't tell me you were going to make me feel old, like right at the beginning.
Joe just said it. But yeah, it's a 40th anniversary. Today is when it opens.
40
The first time I watched it, I was 9.
That means I was...
Oh my God.
Yeah, well, I was...
And you didn't see it in the theaters on opening.
That means I was 14 when it came out in the theaters.
So was I.
Yeah.
I was negative.
Oh,
man.
But you
I
came
was-
up with us, Morgan.
I was 8
Yeah.
and I saw it in the theaters.
Oh gosh, this is crazy. I did too. I saw it in the theaters more
I saw it in
times
the
than I
theater,
want to
too.
admit. I actually paid a lot of money to see, because back then there was no going to DVD or streaming or any of that. You had to go to the theater and watch it if you wanted to see it.
Anyway.
Okay, happy
Moving right along.
happy making Tony feel old day. All right, so with that having all been said, let me. Oh well, actually, Carol, why don't you introduce our hangout to our kind viewers and explain a little bit about what we're doing here?
Sure. So the Hangouts are actually sponsored by the American Astronomical Society and the American Astronautical Society, so scientists and engineers. And we thought it would be a great idea to share what we often do in the science community is we have something called Science Coffee. And we often sit around and talk about other people's papers or sometimes our own. If at my home institution, Space Telescope, we often have visitors who are going to give a colloquium, and they come to coffee as well, and they talk about their research. But we thought it would be fun to do this online with you all and talk to the people who are actually doing the research, rather than having Tony and I every week just talk about what we think about other people's research, because that might not be that interesting. So we want to hear from the people really doing the research, really using NASA missions, really using these great telescopes on the ground, what they're doing, why they're doing it, how they got their data, and what they found out. So welcome to coffee.
That's right. And we want to make sure that all of you participate in our Hangouts. And the best way to do that, we are streaming on 3 different platforms now. I'm streaming on YouTube, twitch.tv/deepastronomy, and facebook.com/deepastronomy. And I am looking at 2 of those 3 live chats here. I've got Twitch up and I've got YouTube up, and my good friend Carl Clark is the driver of the internet. He is behind the curtain right now, and if Judy Garland has taught us anything, we know better than to look behind the curtain. So he's going to be driving us. I'm going to be periodically. He's checking Facebook and Twitter using the hashtag AstroCoffee. So thank you, Carl. And let's get started. So we got Carol. This is amazing. We're talking Cassini today.
I know.
This is like a real get, right? I mean, this
I'm
is
very
huge.
grateful that our guests agreed to do this hangout.
too.
That's really exciting.
Me too.
Anyway.
All right, so let me start by introducing them. So here we have. I'll start with Dr. Scott Edgington. Whoops, I got my clicks all messed up there. Here we go. Dr. Scott Edgington. He is the deputy project scientist for Cassini. Welcome, Scott. It's good to have you here.
Hello, Tony. Nice to be here.
Well, thank you for joining us. Also joining me is Dr. Jo Pitesky. She's the project science. She works in the project science engineering group. She drives Spacecraft. Hi, Joe.
Howdy.
Hi, it's good to have you on our hangout. Thanks for joining us. And also Dr. Morgan Cable. She's the She works the assistant project scientist, I believe, at Systems Engineering. Is that correct?
That's pretty close. Yeah, so stoked to be here. Thanks so much.
All right, well, thank you, Morgan. Okay, well, I want to start. Let's start with you, Scott. Maybe you can tell us, not that there's anybody, I think, that doesn't know what Cassini has been up to. But maybe you could give us a quick summary of what Saturn or what Cassini is doing and for how long it's been doing it.
Okay, well, Cassini was launched in 1997. It took us 7 years to get to Saturn. Flybys by Venus and Earth and Jupiter. And we got there in 2004. We've been there all this time studying various moons in the Saturn system, rings, the planet itself, the magnetic field that surrounds the rings, or the planet. And so back in November of this year, we started pulling in our orbits closer to Saturn and started on our F-ring orbits. And we had 20 orbits that just skimmed grazed the outside of the rings of Saturn. In April, we began our grand finale orbits, which is where we pulled in the periaps, and now we're orbiting with the spacecraft going between the gap, between the rings and the planet, and that we've been doing that every 6.5 days. So every 6.5 days, there's all this excitement here at the lab, wondering, one, did the spacecraft survive? Two, what have we discovered going through the gap that time around?
Now, the first one was it in April? The first fly through the gap, the ring gap, was that back in April? Or is it early May?
April.
Okay, so,
April 20,
and you guys were worried, if I remember the press releases right. You didn't really know for that first flyby what to expect, did you? I mean, you knew there'd be some stuff in there, but you weren't sure if there would be enough, like, grains or rocks or little pebbles in there, so you weren't sure at first, right?
Right. Well, before Cassini, all we had were models that kind of predicted what the dust content in that region would be, and this is where the scientists are imposing various physical effects to track particles that originate from the rings themselves, and then using imaging from Cassini, they look at those images, and to the best of our knowledge, there was no big particles that could scatter enough light to show up in those images. That did not mean that there's nothing there, because the models, of course, were predicting it. And when we flew through the first time, we were in a defensive position where we had the high-gain antenna protecting the spacecraft. This high-gain antenna is about 3 meters across, and it's basically the most solid piece of the spacecraft. So if something hits that, it won't do any damage to other key components. And during that pass, we detected no dust at all.
Yeah, which was a big few, huh? Big sigh of relief. Okay, well, I want to get to the details of the grand finale here in just a bit, but before I do, I want to get some of these other guys in. Joe, can you tell us a little bit about what your role in the mission is? How long have you been working on Cassini, by the way?
I always forget to look this up because the problem is I came on the mission just after we had flown by Jupiter, and I took a short break to work on the SIM mission, which unfortunately went down in budgetary flames, and then I came back to Cassini full-time. So I've probably been here about 13 years in total. I keep track in one way because my youngest daughter was born a year before Cassini launched, so that's kind of how I vaguely keep track of how long I've been here.
Yeah, it's amazing. It's been up there a long time, hasn't it? And what sort of role do you play on the mission?
Well, I've been kind of a jack of all trades. I work right now with the Project Science Office in Project Science Engineering, and that's trying to do the work of herding cats, making sure that all of the science team works well together, making sure there's communication between the science side of the house and the engineering side of the house. Most people tend to think in the general public, scientists and engineers, they're all just geeks. But really, it's two entirely different cultures, and they sometimes don't always play well together.
Oh, really? Science and engineering?
I know.
Yeah. It is like herding cats.
We really do learn to appreciate each other's worlds, and that's been a lot of fun to do. I have also been in charge, or not in charge, I've been one of the people contributing to the science observations and the timeline that we have planned out each time we've flown very close to the moon Titan, which has been absolutely fascinating. We completed 127 close flybys of that moon. We use its gravity in order to adjust the flight path of the spacecraft so that we can look over and under and behind and in front of and all through the Jovian Saturnian system. And I've had to send commands up to the spacecraft. There's nothing like getting what I call a drunk text from the spacecraft at 2 a.m. because she's having some problem. I do a lot of outreach for the project.
It drunk texts you.
I've written, I know, she's really demanding.
Oh, that's hilarious.
And I do outreach both to the technical community and with it for the general community as well. And we also have some outstanding bakers on the project, and I contribute to that as well.
Did you say bakers?
Yes.
You mean like food?
Yes.
Oh. So you
there's
make
some of that on my Twitter feed, actually.
There's project bakers. I love that.
Yes, there are.
Okay. All right. Well,
we have such community.
Yeah, that sounds great. Okay. Well, let me get to. Let me just let me talk a little bit to Morgan. If you could, are you
Hello.
there? There you are. There.
Yes,
Let me just
I
get
am
you up
still
on the
here.
screen. Yes, you are. I'm
Hi.
clicking furiously to get you here. So, hi, Morgan, and maybe you could give us a little bit of an idea of what you're doing on the mission and how long you've been working on it.
Sure. So I'm relatively new to Cassini. I've only been working as a member of the team for the last couple of years. One of the beautiful things about missions that run for this long is that they're able to bring both seasoned experts and then have them mentor people like me as we start off and gain tons of experience and be able to watch this incredible mission and learn from its successes and then be able to apply that to future missions to exciting places. So I assist Joe and Scott and the rest of the project science team as a project science systems engineer. I also, just like Joe, I love to do outreach, so both technical and just to the general public to let them know what their tax dollars are paying for, because we're able to do some incredible things thanks to the community in general. I also get in the lab every now and again, and I'm doing some experiments simulating the surface of Titan. Basically, we make these little mini Titan lakes in the lab, so methane and ethane, and then dissolve stuff in there and try to figure out what kind of chemistry can happen at these really cold temperatures, which then we can compare back to Cassini data. And I'm also part of a proposed follow-on mission that would go back to the Saturn system and would study specifically one moon in particular, Enceladus, which, thanks to Cassini, we know has this subsurface liquid water ocean. It's got this plume spewing out of the South Pole that's giving us all sorts of information about what that ocean is comprised of. And we're hopefully going to look for some of the ingredients of life, or at least whether life could potentially exist in that ocean.
But not with Cassini, right?
Well, Cassini was never meant to be a seafaring mission, and it has some incredibly powerful instruments. Well, I mean, at the time it was state-of-the-art, and it still is the most state-of-the-art piece of equipment in the Saturn system. But since Cassini's development and launch, we have developed a lot more powerful and compact and sensitive instruments, and we're hoping to send some of those to follow on and build on Cassini's amazing discoveries.
Well, now, correct me if I'm wrong, but the discovery of the water plumes on Enceladus, that was a complete surprise. That was unexpected, wasn't it?
Oh my goodness, yes. And Joe can add a little bit to this, but we knew that Enceladus was linked to the E ring, which is one of the rings around Saturn. Now, we weren't sure if Enceladus was feeding the ring or if maybe the ring was doing something in reverse, sort of causing Enceladus to form out of the ring. Since Cassini, we have since discovered that, yes, in fact, Enceladus is what is feeding this E-ring with material from its subsurface liquid water ocean, which we also didn't know existed prior to Cassini. So that's one of our, I would say, our top 10 best discoveries of the entire mission, because this tiny little moon, it's only the size of Arizona, but it's packed with tremendous potential for holding life. It's got those three ingredients that we think are key for life as we know it. It has water, liquid water, it's got energy, and it has chemistry. We found all sorts of organic molecules in that plume. And so if you have all those ingredients and you just mix and stir and wait, hopefully life can take hold. And that's something that we're hoping we can continue to address, that main question: is there life on Enceladus or elsewhere in the Saturn system?
Joe, you want to add something to that?
Well, Morgan started talking about the discovery of the plume, and the astounding thing about the discovery, everybody sees pictures of the plume, so we think that the cameras took a look. But in reality, the plume was first found by our magnetometer, our instrument that measures magnetic fields. And that's important because that tells us something about the interior of bodies, which we can't, of course, look at on our own. And it was the magnetometer that said, we see the magnetic fields around Enceladus, and it looks like something is pushing the magnetic fields around. We think there's a plume, and we want you, Spacecraft Engineering Office, to allow us to go closer so we can check this out.
Yeah, Carl's got a nice picture of the plumes up for us now. So.
And that was the point where the camera said, well, we have generally not wanted to take backlit images of the satellites because that would basically just, we thought, show us something black and uninteresting. But we clearly, but that's the only way you can see the plumes.
Well, some of those backlit images from Cassini are among the most beautiful, it turns out, aren't they?
Yes.
I mean,
yes.
We've all seen that one with Earth in it.
Earth.
It's just,
three of them actually now.
Yeah, they are just stunning. Well, okay. Well, the idea of this, or actually, let me just go. Scott, did you want to add something, perhaps, to this Enceladus discovery? Was it what was your reaction? You're muted, by the way.
Sorry about that.
That's okay. Now we can hear you.
Yeah. Well, I remember those meetings where the magnetometer team said, something's different here. The magnetic field around Enceladus isn't behaving the way we thought it should, and that oftentimes that's the way science happens.
Especially discoveries.
It's like, wow, okay, well, that's surprising. Or and so I remember those meetings and the project just having those discussions. Can we get closer? And of course, the navigation team goes off and looks to see what's possible, because ultimately they're the ones who are steering the spacecraft. And so it was determined that we could fly closer, and so we chose a convenient spot to a spot that would minimize impact to other types of science that we were doing, and flew closer. And then after this discovery, there was all this interest in Enceladus now. And for our first extended mission, we decided, okay, we're going to include more flybys of this tiny little moon and explore it further. And so the next 7 years, the path was paved for exploring Enceladus. You
know what I think? I'm just going to tell you what I think, because one of the reasons I'm so excited about Enceladus is that people are looking for life on Mars. We're hoping to find it, but the chances of cross-contamination are pretty high on Mars. But worlds like Europa and Enceladus, to me, it turns out that there is life on either one of those two moons, but especially Enceladus and Europa, because they are covered in ice. I think that makes a really good case for the life starting from scratch to be a pretty easy one. It makes a good case for that, don't you think? If we find life on Enceladus, chances are pretty high that it probably didn't come from somewhere else, right? Because it's been encased in ice. It's kind of protected.
I can take that out
okay.
For the beginning. That's something that's actually up for debate. I mean, there is a lot of exchange.
No, don't debate. I just said the thing.
Between planets of material. And one of the things that we're interested in, not just for Enceladus, but in particular Europa, is whether or not there's any exchange of stuff that's happening on the surface, moving down and going down into that ocean. On Europa, this would be important. So Europa's around Jupiter, not around Saturn,
right.
Because its neighbor moon Io. Oh, no worries. Europa's neighbor moon Io is spewing its guts out. It's the most volcanically active body in the solar system, and it's sending a lot of material like sulfur-based compounds that are hitting the surface of Europa. Now, there are certain types of bacteria and other forms of life that use compounds just like that for food to generate energy. And so if some of those sulfur-based species are getting pulled down through that icy crust down into the ocean underneath, that could be a potential energy source. Now, in Enceladus, the crust is thinner than it is on Europa, and so the potential for exchange is also there. But Enceladus in particular is so fascinating for us because it's just spewing out free sample. You don't have to dig or drill. All you got to do is fly through it.
The Costco of the solar system.
It totally is. But there are other worlds where these exchange processes might be important too. Titan, which is the largest moon of Saturn, second largest in the solar system. Ganymede's the only one that's bigger. If you count Titan's atmosphere, though, it's the biggest. So, in my heart. But Titan also has a liquid water ocean underneath all the crazy stuff happening on the surface. Most people don't realize this. And Titan's got so many organic molecules. They're forming in the atmosphere from UV radiation and charged particles that are slamming into nitrogen and methane and making all sorts of organic molecules. And then those fall on the surface. But if there's a way for that to get pulled down through Titan's icy crust, down into that liquid water ocean, just imagine all the food that some type of bacteria could have to eat down there.
Yeah, but the life, if there is any there, is going to be pretty darn weird, don't you think, on Titan?
I hope
Maybe.
so.
Yeah, I hope so. Okay, all right, I want to get to a question that.
But I do want to say that it's really amazing how this mission has sort of brought to light all the interactions between these bodies that we originally sort of thought of as being isolated and on their own, and the fact that all this exchange of material is going on. So, yeah, you got the lights back on. Anyway, it's really cool. So it in that context, it makes exchanges between Mars and Earth not seem as far-fetched as they used to.
Which we have. We see meteorites that have come from Mars and have ended up here. I've held a piece of Mars in my hand.
Yeah. So it's amazing. There's a lot going on.
Meteorites on Mars, too, right?
Mm-hmm. Yeah, and they conveniently land right near the rovers, which has been just incredible.
Yeah, thank you, Mars.
Well, they don't have as many meteorite hunters running around picking them up on Mars.
Okay, I need to get to a couple of questions here. Philip W. is asking a question for the panel. Has the amount of time Cassini has been up there helped NASA JPL design probes for future missions better designed and protected? What have you learned about spacecraft design over the life of the Cassini mission?
Well,
who wants to take that?
That's from Philip W., by the way. Thank you, Philip.
Yeah. Well, thank you, Philip. Well, I think one thing that Cassini has shown is having a well-equipped spacecraft can lead to so many discoveries and such a rich science data set. As you might know, NASA has various sizes of missions. We have the Discovery missions, which are kind of the smallest sort of mission that they're willing to fund to send to the outer planets. And then there's the New Frontiers, which is sort of the new, the mid-level type of mission, which has bigger scope and more instruments on board that could do a more thorough job. And then there's the flagship missions, like Galileo, like Cassini, like the Mars landers, the most recent ones that have a full suite of instruments that could do a thorough exploration. Unfortunately, these missions take so long that they were reliant on technology that was developed back in the early 90s, which does all of our work. And just think what you could have now. There's been at least 20, 30 years of development of a lot of the technology. And so,
especially in detectors and things like that. So we really come a long way.
So the Europa mission is going to use the best of the technology.
Now that's that's what's on deck, today. Right? That's what. Yes, that's what's on deck. Yes. Well, let's talk about that a little bit later in the hangout because I want to know if you guys are going to get involved in that. But I want to get to Alexis Desplin's question, but it's a spoiler alert. I guess you guys already know that Cassini is going to end its mission. I think it's in September or October, right? Where September, it goes 15. September, where it goes in crashing it into Saturn itself, and so. That happened. So if you didn't know that, sorry to spoil it for you. Anyway, Alexis is asking, how far into Saturn do we expect Cassini to go before it either stops transmitting or implodes? How far after the first event would the second one happen? I guess stop transmitting and then imploding.
So they're kind of related. We are not really going to get very far because Cassini itself is not a probe. It was not designed to be able to resist heat and friction of the atmosphere as it's going in. So this is kind of a bonus feature that we're getting from the mission. There are proposals actually in the future to do Saturn probes going deeper into the atmosphere, which would give us much more information. What happens is that as the spacecraft enters the last part of its life, then it's going to be sending information only about the Saturn atmosphere. People are really looking forward to getting pictures at that very end, but really the most valuable information is seeing what is Saturn actually made of. So we will be turning off our cameras, and we have finely tuned the way in which data is going to be recorded and immediately spit back out to Earth, so that we're looking at composition. We're looking at the instruments that are more our nose and fingers and ears, if you will, to send us information. So at the same time as we're falling, we are pointing our high gain antenna towards Earth so that we can keep sending that information. And as we fall slightly deeper into the atmosphere starts torquing around the spacecraft. So the spacecraft will be using its little teeny tiny thrusters to try and stay pointing towards Earth.
That's a losing battle, isn't it?
It's going to be a losing battle. And, if we even get a minute or two at a certain point, then it's going to go so fast. And we will be seeing the last little bits of data dribbling down, and then there will be no more.
So no GoPro cameras.
No, not this go round. That would be great for.
If I've learned anything about NASA science missions over the course of my career, is that you guys get the most out of every single possible pixel and second of data that you transmit. Every packet of data has always been maximized. It's just astonishing to me what all the stuff you're able to get done in the course of a mission. And I guess, and John, going back to this first flyby where you were maybe worried a little bit about the particle size, you actually turned Cassini so that the big dish was sort of in front, right? So in case anything big hit it. Is that right?
Yes.
Yeah.
Okay. Now, are you still doing that with the subsequent flybys, or are you pretty confident now you're going to be okay?
There were a few where we had built that in, but one of the worries for that first flyby, because if you hit something going 77,000 miles an hour, it ruins your whole day.
It does.
So the worry had been that if we found a very substantial particle environment, we would have had to go back and change our science and change the orientation of the spacecraft so that it was always pointing kind of like a cowcatcher on a locomotive in a way. And we don't have to do that. Yay!
Because that's scary, isn't it? I mean, I've often wondered this about with Hubble as well. Whenever you got to move that thing, and you're talking about getting drunk texts from Cassini earlier, Joe, that's got to be scary whenever you send any kind of command to move the spacecraft, especially when it means you're going to lose contact, right?
Nah, we're used to it by now.
Are you? It's no big deal now? Oh, okay.
It's doing something for the first time is the scary part.
I'd hate to be the guy pointing Hubble. That's all I'm going to say. I don't want to. I know they got it down. They've been doing it for 7 years. I know they got it, but still, that's a lot of stress. Same with driving rovers. I don't think.
So did you all call New Horizons and said, "Oh, get a grip, cowboy up, people."
Cowboy up. We do this every day before 9 a.m.
Yeah. Unfortunately, New Horizons only had one shot. If they missed Pluto.
That would have been a bummer, all right.
Yeah. So I like to add to Joe's comments about the final moments of the spacecraft.
Okay.
So we're going to be literally in the upper atmosphere. You're talking well above where, say, spacecraft or airplanes would fly. That's where we're going to lose contact. And then as you enter the atmosphere, things will start falling off, melting. And eventually, the bulk of Cassini is aluminum. And so that aluminum is going to end up where the atmospheric density is equivalent to aluminum.
Cool. Well, let's see. Stargazer Girl 30 is commenting, this is the only mission that I've followed from launch on to now. I've really become fascinated with Saturn and its moons because of Cassini. Do you find there's a lot of big fan base out there for Cassini?
Oh, yes.
Oh, yes.
Yeah.
Just look at our Twitter account.
I do look at it. Yeah. So I mean, everybody is like, why can't you save it? What's the reason for it? You really are done. There's really nothing more that can be done with Cassini at this point, right?
Well,
the reason for not being able to keep the mission going is because we're basically out of fuel,
right.
And we use that fuel to steer the spacecraft. As we fly by Titan, we tweak the trajectory to get to our next destination, and so everything's finely tuned to do that. When you're out of fuel, you are at the mercy of gravity and whatever body you're flying by, and then we are a victim of our own success. Discovering that Enceladus could be a habitable world, and Titan, in addition to that, basically we have to protect those worlds, and just keeping the spacecraft out there to let it, float around according to gravity, having Newton determine where we're going. There's always the chance that we could smack into those bodies.
Yeah, that's
there's
really
actually
important
a
point.
whole department in NASA called Planetary Protection.
Yep,
I know
we've
they
talked
don't
to some
wear
of the
capes.
members. Yeah,
I asked. But
Yeah,
they
so
have two big goals. One is to make sure we don't bring anything dangerous back to Earth, and the second large goal is to make sure that we don't bring any hitchhikers on our spacecraft and deposit them somewhere else. And so that's why every NASA spacecraft has a disposal plan at the end of its mission, which is a very sad event, but a very important one to make sure we don't contaminate, like Scott said, some of these habitable worlds that we're discovering in the outer solar system.
But Saturn, the heck with it.
Whatever it picked up from Enceladus, it just dumped into the upper atmosphere of Saturn. So there we go. Cello Fingers is commenting, Carolyn Porco should get many kudos for her pioneering work as former head of the Cassini imaging team. Many great discoveries were done on her watch. That's a good comment.
Absolutely. It's been an incredible team, and this is a mission that is comprised of multiple instruments, which have made incredible discoveries on their own, and also have made discoveries that have reinforced and learned from each other. The Enceladus plume is just one of the absolute tremendous, notable examples of that. And a lot of the science that we're going to be doing, finishing up the mission, really depends on the cameras in both the visible wavelengths, like Dr. Porco's instrument, as well as the infrared and the infrared cameras and some of the spectrometers, which are able to take a look at different parts of the spectrum as well. And that's not even getting into what we call the fields and particles instruments, the radar instrument, which was able to give us a map of the surface of Titan in incredible detail because of its ability to penetrate through the thick methane clouds surrounding that moon. The radio science instrument, which is really an experiment separated by 1 billion miles. It depends on both the spacecraft itself and on the Deep Space Network antennas here on Earth. And that's been able to tell us a great deal about the interior of many of these bodies, and has told us something about their atmospheres. And we are hoping at the very end of the mission will give us some insight into one of the real fundamental questions we don't understand, which is, where did the rings come from? And in order to know that, we want to know how old they are. And one of the ways we can help pin that down, without looking at their birth certificate, is by getting a sense of the mass of the rings, which we haven't been able to measure yet. And so this grand finale is going to allow us, by going into the gap, to hopefully extract that data. So this has been a team enterprise.
And there's 20, yes, definitely.
It takes a village to do this work, and that's the advantage of having a flagship mission. It's not all about pretty pictures. It's all these different instruments contributing, and they all contribute pieces to the puzzle, which leads to the remarkable discoveries that we've made.
Scott, what was the original mission length for Cassini? How long was it supposed to last initially?
We were guaranteed for 4 years, and then after that, it was anyone's guess.
Has any NASA mission ever just done the basic mission? I mean, I can't think of a single one. That's great. So you went well beyond that then.
Yes, and in the middle of that, 4 years, of course, you're thinking about what's the future of your spacecraft. And with the mounting discoveries that we were making, and the fact that we had enough fuel to keep going, our engineers went off, and the navigators did study after study, and came back to the scientists and said, okay, well, here's 5 different things, tours that we could fly. And oh yeah, by the way, we've learned things. Instead of just 4 years, we could take us another 7, 8 years. And so, when they showed us the grand finale and the fact that we could observe Saturn for a whole season, the scientists were just like, yes, let's do this. This is the best thing to do with the spacecraft.
Yeah, we're very good at over-engineering our spacecraft here at NASA, but I think one of the greatest advantages of being able to extend this mission, and we did have to go to NASA headquarters and make the science case that it was worth continuing this amazing mission. For example, seasons on Titan. Titan's year lasts much, much longer than Earth's year. And because Cassini has been able to stay in the Saturn system and observe Titan for 12 years now, we're watching the seasons change on Titan, something we could not have done just in the initial 4 years of the mission. And we're learning much more about the dynamics of this fascinating moon because of that.
Yeah, you know what I think though. I think you engineers do this on purpose, because what you do is you go, we've got a mission, and we know the limiting factor is going to be the fuel. So why don't we they say 4 years, but let's really put in 11 years worth. You guys, right? I mean, come on.
Okay, I got margin just in case.
Yeah, that's right. Because and the same happened with. Kepler. They had to resubmit to extend their mission, which of course they did as K2. So, okay, a couple more questions. George Caldwell is asking, did Cassini get any new information on the eventual erosion disappearance of Saturn's rings?
Yes and no. There's a big debate as to how old are the rings? Are they young, meaning that an object ventured too close to Saturn and was broken up and created the ring system? Or are these rings the remnants of a bigger ring system that existed, from which the moons formed? And so that's we've been talking about that a lot of late, especially as we're executing these grand finale orbits. One of the key pieces of information we don't have is the mass of the rings, but flying in between Saturn and the rings, we could look at that gravity signature and determine just how much the rings are pulling on the spacecraft in the opposite direction from Saturn. And so once we determine that mass, that will help us learn something about that. In addition, our magnetometers, our plasma instruments, they have detected a quote-unquote atmosphere above the rings, so we know that molecules are slowly escaping from the ring particles and creating its own plasma just surrounding the rings, and so we're learning about that. We're also looking at details within the rings that shows how structures form, come together, evolve, and maybe break up. In fact, one object, Peggy, we've seen that for a few years now, and we're kind of hoping that it stays together and forms a moon unto itself, and maybe detaches itself from the ring system. So there's all these studies going on, and it's still an open book. Cassini has brought back tons of data that's going to be looked at for the next 20, 30 years or more, and scientists are going to, a new generation of scientists will come along and look at that data and determine what surprises are located in that data.
Okay, well, he's also asking another really good question. Now, I know that Cassini, compared to the age of the solar system, has only been up there a blink of an eye, but he's asking, is there any new evidence of how Saturn's orbit has potentially changed over the period of the solar system? Have you gotten any information on maybe some of the historical orbital changes, if any, while you've been up there?
I don't know of anything. I got nothing here.
You got nothing?
Yeah, it's...
Go ahead, Scott.
Yeah, if anything, we've learned precisely where Saturn is in its orbit, but this is only for this 13-year arc that we know this, and so extrapolating in any other direction is, still, especially billions of years, is a bit tricky.
But one of the great things we have been able to do is think of Saturn as if it is its own little mini solar system. So looking at how Saturn and its rings have formed and how its moons have interacted over time, and trying to understand how that came to be and how it's evolving can give us some clues about how our original solar system formed. So we are looking at Saturn as sort of a model for our solar system in general that way.
Okay, Alexis Desplend, again, is asking, and it's a good question, what do you expect to learn from the Cassini crash? What are you guys hoping to see?
We've already...
Any predictions? Are you guys like taking a pool or?
There's a betting pool on the ring mass, actually.
Is there?
Mm-hmm.
Yes, there is.
Yeah, and I'm sure there's going to be a poll on the last moment that we, see the last bit coming down.
You mean like the time of the last transmission?
That timing of the last bit, yeah.
We could bet on the last instrument.
Oh, yeah, maybe.
Oh, you're betting on the last instrument, too.
We should talk about it.
We haven't yet, but we can.
We should, yeah.
But there's a limited number of entries.
Yeah, Joe was talking a little earlier about the Deep Space Network. That is sort of NASA's internet. Well, it's not just NASA's, but other countries use it as well.
The interplanetary internet?
That's right, the interplanetary internet. And it's getting an upgrade, isn't it, the Deep Space Network, isn't it? So the throughput can be better because these new future missions are taking they're going to be taking a lot more data and need a little more throughput. So what about that? What is, I'm curious because I process data and I love data that come off of telescopes. What is an average data dump for Cassini?
Not enough.
Not well, okay, but what do you generally get on what's a typical day's observations and engineering data? All of it. What is it? How much is it?
3 gig.
That's all?
Exactly.
Wow.
Saturn's very far away.
well, 3 gigabits, not bytes.
Okay. But
we operate in bits and not bytes.
Do you guys compress that at all on the spacecraft, or is it just raw data?
A little.
So you do compress
it depends on the instrument. It depends on the instrument.
And
some instruments have the ability to compress, like for example, the imaging cameras. They can do some compression of their 2D instruments or data. The other instruments may or may not have a compression algorithm.
Okay. Wow, that sounds much.
So let me tell a little story about how sometimes data compression can work or not work in unexpected ways.
I think I know where you're going. Go ahead.
So we had a was it? No, it was the visual infrared spectrometer that was planning on looking at an occultation where you are looking at you're sending a signal to the Earth, or you're looking at the Earth or a star coming through the atmosphere of either Saturn, sometimes Titan, sometimes the rings. And in this case, the camera was supposed to lock on a certain way on a specific bright target, which was supposed to be the star. Unfortunately, there was a cosmic ray hit, and the camera, being only as intelligent as we make it, said, well, clearly this bright thing is what I should be looking at, and it adjusted just a little bit, not in pointing, but more in what was being tracked. So instead of looking at empty space, which would have compressed very efficiently, it ended up capturing part of the rings. And so that meant that a later observation on that same instrument did not because the compression did not work as well, the observation that accidentally captured the rings, ended up taking up too much room. And a very important observation shortly after that, there was no room at the end, and it was lost.
Wow. So you guys really plan it out, don't you?
This we couldn't have planned for.
No, I know, but I'm talking about your observations are planned out to a degree that if one of them isn't compressed enough, it messes up everything that follows, or a lot of things that follow.
We have a little bit of slack in there, but, we can't leave too much because then we are just leaving science behind.
That's amazing.
I know.
Yeah, and 3 sigma events. Yeah, you really can't do anything or much with 3 sigma events like this.
Yeah, but it's a good story.
Mm-hmm.
Oh wow, that is crazy. Okay, so let's regarding George Caldwell is asking regarding Saturn's atmosphere. Could we find any evidence of Saturn having a small internal heat source, a little like a failed brown dwarf? Would you expect a lot of hydrogen and helium?
Yeah, Saturn just isn't massive enough.
Just not doing it.
No,
okay.
No, it's a small fraction of Jupiter's mass, and Jupiter would have to be 10 times its size in order to be considered a brown dwarf.
Oh, okay. Carl, I'm going to get to you real quick. Are you seeing anything on Twitter or Facebook? Any questions there?
There aren't. Doesn't look like there's any questions on Facebook or Twitter. Twitch is pretty quiet. But there was a couple ones that I thought were interesting, though. You got the small, cooler Thorn zip cob object of Saturn question that George Caldwell asked. I thought that was a cool concept. But there are 2 questions here that I'll kind of combine into one. So for any future mission planning to Enceladus or Titan, what would be the primary goal of those missions, and would CubeSats be able to be used to probe other targets or maybe get faster plotting on things? So you send a probe out, then it deploys a bunch of smaller CubeSats, and you have a whole network up there.
So I can take this one.
Morgan.
She's been ready for this one.
Like, all right, this is what I've been thinking about. Awesome.
Yeah, so thanks to Cassini and other observations by other spacecraft, we now know that there are this whole class of moon that we call ocean worlds that exist mostly in the outer solar system. Now, these typically are moons like Enceladus, Europa, or Titan that have some type of icy crust, and underneath that, usually a global liquid water subsurface ocean. Now, of those, we're particularly interested in ones where that liquid water ocean may be in contact with the rocky core of that moon. And the reason that we're interested in that is because hydrothermal vents here on Earth at the ocean floor are places where you have access to energy, heat, usually geothermal heat that's coming up from that rocky core and is able to interact with water. And we find at places here on Earth that there are rich, diverse communities of organisms that use that energy to exist. And so they don't need any sunlight at all to survive. They just rely on energy supplied from that planet or that moon's core. And so Enceladus and Europa in particular are very interesting to us because if they could potentially have hydrothermal vents down at the base of these oceans, they could have a perfect place where life could either evolve on its own maybe, or if life were transmitted like we talked about before in between bodies. There are certain types of bacteria that could survive an interplanetary journey. Then maybe life could get a foothold that way. So these ocean worlds like Enceladus and Titan are really interesting. And because of that, NASA has started looking at the advent of an ocean worlds program, similar to the Mars program that we already have in existence. It's one of the reasons why we've been able to send many missions sort of in a cadence to Mars, and each one builds upon the discoveries of the previous one. Now, with ocean worlds, it'll be a little different because there aren't just one, right? There are many. And each of them has a different flavor and may require a different type of mission. But this New Frontiers program that Scott mentioned, this is what the New Horizons mission, for example, is one of these medium-class missions. Mm-hmm. Proposals just went in for this. I believe there were like 12 proposals, and to my knowledge, at least a couple proposed missions to Enceladus, and at least another couple more proposed missions to Titan. So these are two big targets that we may end up sending a future New Frontiers mission to if it's selected. So right now those proposals are being reviewed by review panels, and they'll rank them, and some of them will be selected to get a little bit of funding to do what they call go to step 2. And those subset of those mission concepts will get a little bit of funding to develop their story and their plan a little bit more. And ultimately, one or maybe more could be selected that will become real missions. And so the next few years, I think, will be very exciting in terms of exploring these ocean worlds. But the main goals are to look for habitability. So is this place a place where life as we know it, or maybe life as we don't know it, in the case of Titan, could exist? And then the second goal would be to look for life itself, or evidence of life itself. And so I think this will be something that you'll be hearing more and more about as those kind of concepts get further developed.
Golden age, folks, not just of astronomy, but in planetary exploration. Can you imagine?
It's a really exciting time to be a planetary scientist, let me tell you.
Yeah. Go ahead, Scott.
And a lot of the new discoveries from Cassini has paved the way for this program. It used to be thought that you look for habitable planets by looking where they are relative to their star. Is it too close or too far? Well, you rule those out, and then you have the Goldilocks zone. But thanks to Cassini, we have many Goldilocks zones.
So there's another question here that we kind of touched on, but there's something hidden in it that I think is very interesting. If you look at the evolution of life on Earth and then try and compare the time frame of Earth's formation and when life first started to, say, Titan or Enceladus, and how old those moons are, and where we might be able to extrapolate, if there is life there, the possible complexity levels of that life, just using Earth as a semi-analog, particularly when it comes to the chemosynthesis life forms that we find in the ocean vents. I was wondering, Alexander Reinders, or Reminder, I'm mispronouncing that name, I'm sorry, Alexander, but that's kind of what they were talking about.
Okay, I can take this one.
Okay.
So yes, it's very hard to figure out how long it takes life to evolve, because we only have one example, right? Us, and we can only go back so far in the rock record here on Earth. But if you look at the literature, let's say that you have all of the ingredients, right? You've got the organic molecules, you've got liquid water, you've got an energy source, and you just mix and wait. How long does it take for life to exist? And if you go through and scour the literature, which I've done, it's about, most people would agree, within 10 million years or so, something will have happened. Which isn't that long, actually. I mean, you consider how old the solar system is.
Hang on. You just said that if all you have is a bunch of stuff that isn't as primordial soup, and you've got energy, and you've got all the basic building blocks of life, but not life, and you wait about 10 million years, something alive will happen.
Now, there's still a lot of contention amongst the scientific community about whether that's true or not. But if you look at Earth's history, we've had several major extinction events where life basically was cut down to nothing and had to start over again. I mean, for all we know, our last universal common ancestor, Luca, it looks like it was a thermophile, which is heat-loving, right? So that means that the conditions had to be right for that sort of organism to come and then generate. That's the tree from which all life as we know it sprung, but that doesn't mean it was the first one. There probably were several stops and starts along the way. And so if you look at the ages of some of these moons, Enceladus probably has had this liquid water ocean for at least 3 times that 10 million year mark. And Europa has been around much longer than that. So there are places where liquid water has been stable long enough that we think that life could exist, or could have had time to form, if you believe what is currently present in the literature.
I want to read that literature.
Mm-hmm. And yet, we should be prepared to be surprised. I'm thinking about when the first exoplanets were found, and I had gone to grad school, and we had talked about this is how a solar system forms, because look, you have small planets in very close to their central star, and you have large planets that are further out, so therefore the model must be blah, blah, blah. And the very first exoplanets that were found were enormous super Jupiter-sized planets, even larger than Jupiter, orbiting incredibly close into their central stars. Where in the world did that come from? So we can have our models, and then we also need to be prepared, hopefully, to see them entirely blown up.
I think
Well, I think
Scott
that's
may have to
borne
drop
out by
off
the history.
quickly. Scott, do you want to say a couple words before you have to go to your meeting?
Well, actually, I'm running out of power.
I'm trying to cover for you, Scott.
Before you go to your meeting and his battery's running out.
But it's also good that you did remind me that I do have another meeting, as my phone is now telling me. I just want to say Cassini has been an awesome mission. 13 years around Saturn. We've been there for an entire season and more, and we've learned so much about the system, each object in the system, how they interplay with each other, and having a capable spacecraft that could do all these experiments and bring back this knowledge is invaluable. And I hope that NASA continues to fund missions like this. And if you and your audience believe in this, write your Congress people, because they will listen to you if you write them and support space science. And we need all the help we could get to keep NASA healthy and continue exploring.
That's right, and as we've seen success, well said, we've seen success after success from the NASA missions, and so we hope to see a lot more like this. So thank you, Scott, for taking time out to join us. If you've got to go, just hit the little red phone there, and you'll leave the hangout. But since we've only got a couple of minutes left, let me ask my remaining guests, Joe and Morgan, what can we expect over the next few months with Cassini? We know that it's going to crash in, but maybe you can give us a very brief summary of. You had a total, I think, of 22 orbits between
Correct.
the rings, and you've done some of them already. Are we just going to keep doing this until September?
Yep, about once a week we plunge through the gap that is separating the uppermost atmosphere of Saturn from the innermost edge of the rings. We are going to be moving around a little bit in that just because Sir Isaac Newton is driving right now, and this is the way it came out. So we will actually be going through some of the, a little more into that innermost D-ring edge. And people can certainly follow along the website saturn.jpl.nasa.gov.
Yes,
there's
definitely.
raw images, and every time there's a downlink, it's just like was in The Martian, where they were asked, well, can't we cover up this evidence that the astronaut is still alive? No, NASA is obligated to release all data within 24 hours of receipt. That's absolutely true. So all of the raw images that appear get posted to our website. And right now we're seeing images coming up from Titan. That was from the downlink that was sent to Earth yesterday. Before that, we were seeing images of Saturn. You can go flipping back through this. This is all uncalibrated. But on Twitter, especially if you follow along at, for example, hashtag Cassini Inspires, and if you look at some of the other things that amateur planetary scientists are doing, you can see astounding work that people are doing, putting together animations. We have our last flyby, I'm trying to remember, is it Iapetus, I think, on next Tuesday?
Oh.
Our last close encounter. We have a last and bests that we keep track of, and we're just kind of waving goodbye.
Yeah,
So
it's just the last of everything.
we're just prepared to see a lot of really great imagery. And as people start going through their data reduction, we're going to be seeing some amazing images coming up as well.
I gotta read these comments because they're funny. A lot of my viewers that watch these hangouts live are actually in the UK, and George Caldwell is like, I would write to my congressman, but I live in the UK, and he also says, and Parliament is dissolved. But John Suffel goes, I'd write to my MP, but I don't think he can read. So anyway, yeah.
Well,
so
remember, Cassini is actually a joint mission between the European Space Agency, NASA, the Italian Space Agency. I mean, ISRO. This has been, or not ISRO. Sorry, the ASI. Thank you. It's been an amazing collaboration. So the ESA is a very critical part of what we do, and we're happy to continue to collaborate with them on future missions.
yes. All right. Well, I'm going to have to call it there because we are out of time. I want to thank my guests.
Yes, thank you very much.
Yes, thank you very much, Dr. Joe Pitesky. She's a project science engineer on the Cassini mission. Dr. Morgan Cable, the assistant project scientist in system engineering, and Dr. Scott Edgington, the deputy project scientist for Cassini. Thank you all so much for taking time out.
I wanted to say happy Saturn solstice, and
Thank you.
for the UK people, mind the gap.
Well, thank you all so much. This was really insanely interesting, particularly the links of planetary science and earth science and all that good stuff. So raise the coffee to you, and may the force be with you all.
That's right. All right. Thank you all very much. I appreciate it.
Thank you so much.
Yes. All right. Well,
thank you for your time. I really appreciate it.
Yes, and so keep your eyes
now
on the.
Off to your meeting, Scott.
Yes, off to your meeting.
Yes. Okay, I'll go back to my meeting. Yeah, okay, bye.
All right. So on behalf of all of our guests and Carol Christian, I want to thank you all very much for watching. Next week is the Footsteps to Mars hangout with Dr. Harley Thronson. I think we're going to have an astronaut there to talk about the human physiology of space. We're still confirming that, so I won't say her name yet. But we hopefully that'll happen. So that's next week. We'll see you there. On behalf of Carol Christian, thank you all so much for watching. And as always, keep looking up.